Hi, folks. So today we're going to talk about machine learning. In particular, we're going to think a little bit about what it means to actually collect and use data for machine learning, and then go through the different classes of machine learning, including supervised, unsupervised, and reinforcement learning, to kind of give us a framework for thinking about the different ways in which we create learning algorithms that are the fundamental component of AI systems. So let's dig in. We've been collecting a lot of data over the last few decades. A lot of this data is human-produced content, and it's published on the internet, and it represents all sorts of different aspects of what it means to be human, right? This project, the sentiment analysis project called We Feel Fine, collected over 3 years of data from personal blogs on the internet, and it gave us a really interesting insight into the world's emotional landscape, right? So all of the chaos, all of the feelings, all of the things that we have decided are totally okay for us to share publicly on the internet. You can see in this particular analysis how you could actually track the way in which people were feeling depending on their age group, on the time of day, on their gender, on the weather even, in different locations. And so we can actually do things like sentiment analysis on the different kinds of data that we have produced about ourselves out in the world. One of these papers I thought was at least a little bit interesting for us to kind of look at, to just understand a little bit more about what is valuable, what is powerful about this data in the aggregate, right? So in this particular case, they analyze emotions expressed as people age. And so you can see how people feel, how old, how different age groups feel with respect to anticipation, to joy. You see people feeling less surprised as they get older, feeling a little bit less disgust as they get older, and even sometimes feeling a little bit more acceptance as they get older. And so the data that we produce about us is a really powerful insight into what it actually means to be human. These data are particularly important as they also are the training data that we use for different kinds of AI models, right? So these volumes of data represent the different types of examples that we are using to teach AI about what it means to be human, right? Here's another example of a time series analysis of emotions, and you can see people feeling more proud and excited when Obama got elected, and a little bit lonely and sometimes special on Valentine's Day, and feeling a little bit more and less stressed out as the week progresses, right? And so we're actually able to learn a lot about the way in which humans present themselves, the way in which we think, the rationale for the different feelings that we have. And again, right, this is really rich fodder when we're starting to think about how to actually teach different kinds of machine learning algorithms, how to emulate human thinking, human behavior, and sometimes even human emotions. The goal when it comes to thinking about what to do with all of this data is really to be able to sort of go through this data science stack of taking this glob of data, right? That mess of human emotion, beginning to sort it, arrange it. Yes, present it visually so we can kind of interrogate a little bit, but really it becomes particularly powerful when we're able to take that data and use it to tell stories and be able to actually do useful things. And so when we talk about big data, a lot of folks will talk about the 6 V's of big data, right? There's volume, which is the sheer quantity. There's variety, which is the different kinds of data. There's velocity, which is the speed at which data is generated, right? This is particularly important as we start to use more and more IoT systems to collect data, right? So streaming video data from CCTV cameras across a city are high velocity, high volume, and high variety, right? We also talk about concepts related to veracity, which has more to do with the trust that we have in the different kinds of data that we collect, right? This has implications for ideas around misinformation and what does it mean to actually trust models that have been trained on different kinds of data that we may or may not trust. And then we also talk about things like value with respect to data, which is a little bit squishier in my mind because it's sometimes hard to actually define what it means for data to be valuable when we haven't yet used it in a particular context. And so there are lots of different ways in which we can think about big data, but really the take-home message that I'm hoping you're kind of sitting with right now is that we are producing a lot of data across a lot of different sectors, right? We're beginning to produce petabytes of data, not just about human emotion, but for each of these individual sectors, right? So if you look here, you can kind of see the way in which the data that we've stored in manufacturing, in government, about banking, about healthcare has dramatically increased over time, right? Big data really then allows for us to kind of think about how can we improve or find insights or really interrogate very specific parts of human society, right? So in this particular case, we're looking at an example of projections about what big data can do to improve the manufacturing value chain in terms of cost, revenue, and working capital, right? And so a lot of what we were doing early on with machine learning was really trying to start to make sense of this incredibly diverse and complex data that we were collecting about the world around us, not just about ourselves, but about our systems and about the environment as well. This poses some really interesting challenges. This was a beautiful art piece that actually came out in the New York Times, and where Jonathan Harris had sort of described some of the challenges with data, right? Data will help us remember, but will it let us forget? If you read through some of these examples, he reflects on the different ways in which data can be really powerful, but also create problematic issues as we start to think about, it will help parents make kids genetically perfect, but will help us love them regardless. There are lots of complexities when we start to think about what it actually means to use data to make humans better, to make our world better, because we're really, again, imbuing it with certain sort of like directions, right? And so I want you to just kind of think about the power of big data and really think about that this is the fundamental ingredient of most machine learning algorithms. And so being really thoughtful about our data, really thinking about the variety of data that we're collecting, I suspect will help you become a more well-informed machine learning designer. So the data science process, right, is a little bit straightforward if you just think about it in terms of you're just collecting, transforming, and using data to be able to then do things like informed decision-making, derive knowledge, find meaning. But the process can sometimes be a little bit esoteric. I want you to kind of abstract away from this and worry less about the details of exactly how data is being transformed as it goes through the sort of spaghetti data science process, but really just understand that once we have collected data, it has to be contextualized, it has to be cleaned, it has to be processed using all sorts of methods. And again, at every single one of those steps, we are there's an opportunity for us to either introduce bias or reduce bias to be able to think about annotating with important context and so on and so forth, right? And so as we kind of think about what a sensible data science lifecycle might look like, you really want to start to think about, right, this iterative process where your data is not this static artifact, but it's really this dynamic thing that you are planning ahead, you're processing as it comes through, and you're really then thinking about how to also do quality control and documentation with these very large data sets that are going to ultimately drive your machine learning and AI systems. There's one last concept I want to talk about on this topic, and it's this idea of fair data that's findable, accessible, interoperable, and reusable data. This is a concept that has been increasingly important in the data science world, especially as we start to think about, there are so many different kinds of data that we've collected. Oftentimes, they're in volumes of books. They might be sitting on some research computer in a lab somewhere. And so there's a really big push in being able to make sure that as we produce more data, it is machine readable, human readable, right? So it's something that I can actually then start to scrape and use, that it's interoperable so that as I move from one system to another, as I train one model and then take those outputs to another, I'm kind of able to sort of carry that context, right? So thinking about the interoperability and reusability of data are, again, really important things for you at least note in the back of your head as you're thinking about that foundational data that models are built upon. Right, so data-driven machine learning is really what we're talking about here. The data points that have been used to train artificial intelligence systems have exponentially increased over time, right? We went from 100 individual data points in some of these early models in the 1950s to 1 trillion data points, right? And these sound like very abstract concepts when I put it like this, but again, remember, this is, right, the photos that you stick on the internet of your cats, right? That's the data that we're using to train our cat identification algorithms, right? And so it means that we have a lot of really rich data out there. And now the question becomes, how do we actually start to use it productively, ethically, responsibly to be able to create different kinds of domain-specific artificial intelligence systems? So what other kinds of data that we have at our disposal? I'm going to run through a couple of really quick foundational data sets that people have used to train machine learning models. So the first one really was WordNet. WordNet was a text data set. This was literally a set of terms and the relationships among them. You could think of this as a dictionary with a little bit of linking among the terms, right? And this allows for us to basically say, what does bread look like? Bread is represented by this, it means this, and bread can be used in these different contexts. I can use bread to say, bread the pork chops before frying them, or I can use bread to say, give me that bread because I did a lot of work. And so there are different ways in which you can kind of use these terms, and these data sets help you kind of, train your model to understand those semantic relationships among the terms. From there, things kind of took off, right? There was an image data set. This is ImageNet. This was one of the largest foundational image data sets. There was this ontological structure that was based on WordNet, and really you could use it to then, right, take all of the thousands of images, millions of images of dogs on the internet and start to then be able to say, okay, this one's a German Shepherd, this one's a poodle, this one's totally fake. Then we started this sort of like trend towards, the ImageNet of X. And so now pretty much whatever you want, there is a data set for it with some caveats, right? So there's SpaceNet and MusicNet and the medical ImageNet, right? Which was used to be able to train radiology or image recognition algorithms in that space. So there's a lot of different now domain-specific data sets, right? Because it turns out that when you start to actually train models in some of these images, you might need some specificity. And that specificity becomes really important as we start to think about interconnected data sets. So this is a snapshot from BabelNet, which was an early effort in trying to actually now start to integrate all of these different kinds of data sets that we have that, again, are being used to train machine learning models downstream. And it allows for us to now start to think about, okay, not just interconnected data sets, but even within a single type of data, how much complexity is there and how can I then unpack that to create more complex data sets, right? So in this particular example, this is sort of like the progression of the work that started with ImageNet. So Li Fei is one of the sort of, stellar researchers in the space. This is one of her papers. You can kind of see with one single image, you have a lot of different kinds of data encoded. And so this image is not just people skiing, but it's also, a picture demonstrating different kinds of equipment, different kinds of clothing, different kinds of environments. And so there are different things that you can look for in this specific image and ultimately train for when you're trying to use this image as a teaching tool, in effect, for, right, a sequence of machine learning algorithms. So as we start to have a lot of different kinds of data, it also means that there's a really there's a growing need for different kinds of beginner machine learning data sets. I will never tell the story without starting with Iris. I think, like me, many people start with the Iris data set. It was on the University of California, Irvine's machine learning repository. And so if you're looking for, small data sets to just kind of kick around and, do your first classifier with, this was the data set that I used to build my first classifier when I was an undergrad. And so there's a lot of really good beginner machine learning data sets. And not to say that they're good for just that, right? These are foundational data sets for then us to be able to think about education and competition. So Kaggle is a data science portal where a lot of machine learning competitions happen, right? Again, if you're thinking about this in the context of education, we actually have our students participating in these competitions. But then within companies, people actually send small teams of software engineers to go kick around a data set, right? It also means that if you're a company interested in bridging that gap to education, you can produce a specific data set, publish it on a system like Kaggle, and then actually invite the public to come and start to tinker with different kinds of models with your specific data set, right? So there's a lot of opportunity for cross-pollination across these different spaces. As we're kind of thinking about now, right, there's so many different data sets. A lot of them have been foundational for developing these machine learning algorithms. A lot of them are really important for education. There's also a growing need for us to be able to have these more complete research data sets. So MINST, for example, is considered a canonical data set of handwritten digits. It is your gold standard. And so it means that if you want to benchmark a model, you will probably want to come to one of these that have been vetted, validated, evaluated, kicked around more than you can even imagine, and are really great for, again, benchmarking your models as you think about how well they perform, not just in the wild, but also in these controlled environments in effect. As we've kind of been thinking about open data, a lot of governments have also begun producing open government data sets. I work in agriculture in my day job. And so for me, these are really rich sources to be able to get information about actual information about the world around us, whether it's in my case, I'm usually looking for things, fruit and vegetable prices, who's growing what. But there's also data about, crime and where different kinds of funding is going and what the different interventions in our society look like. And so again, I bring this to you not because this is the core focus of this lecture, but because these are valuable and important ingredients that you should be looking at as you're thinking about what data should I be using to engage in data-driven machine learning. And so as we kind of close out this piece, I want to point out a couple of what I'm going to call machine learning ready data sets. So this is the Hugging Face portal. A lot of folks will come here to actually spin up different kinds of machine learning models, but you can also come here for these ML ready data sets because they have been pre-processed, cleaned, contextualized. All that prior work has been done so that you're really dealing with a data set that you can kind of just quickly run through a model, as we'll see in some of the subsequent examples. Yeah. Really, we're kind of moving towards this sort of transition towards that semantic web. And we've talked about this before, right? But the power of these hypertext links is that anything could be able to connect to anything. And we thought that the semantic web was not something that we were going to achieve. But again, as we are beginning to produce all these data sets to be able to verify them, so make them findable, accessible, interoperable, and reusable, we're able to now start to literally connect concepts about the world around us, Connect human knowledge. This is an example from DBpedia, and this is a single entry on the Sing pen, And so in this case, we're taking this ontological approach to representing data about the world around us. So a pen, the humble pen, is more than just this writing tool. It is this node in this larger network, in this larger semantic web. And so it's not just a single thing, but it is part of this, this representation of our way of thinking about the world around us, So when we're going back to knowledge representation from earlier in one of the previous lectures, you can kind of think of this as the evolution of knowledge representation that, again, ultimately allows for us to do far more interesting cross-concept analyses, So you don't just look at, how many cats are in the picture, but you're really able to ask more complex questions of the data around you. Okay. This is really fundamental to a lot of the tools that we're going to encounter in the rest of this lecture. I want you to think about this concept of the internet as a data set. And the classic example of this is the Common Crawl, So if any of you have played with ChatGPT, OpenAI's large language model, it was initially trained on the Common Crawl data set, where the Common Crawl was basically a snapshot of the entire internet, That's 3.35 billion pages, 454 terabytes of data as of 2023, This is an ongoing thing, And I should caveat with ChatGPT was not necessarily trained on this specific snapshot. It was trained on a snapshot, But this is the kind of data that we are using to train some of these very, very large models. And so it's important to keep track, keep an eye out, and kind of keep your own inventory of the data sets that are going to be valuable for you in your specific line of work. So now let's turn to actual machine learning and the different kinds of learning mechanisms that are out there. So if we look at a high-level architecture of an expert system, and you may have seen this before, we're really talking about these four fundamental pieces in the center. Experts help us build these knowledge bases, so that data is represented in particular ways based on our understanding and ontological engineering approaches. After you have created a knowledge base, really there must be some sort of inference engine, something to reason, and then there's a user interface for people to actually be able to engage with this inference engine. A big part of closing this loop is the development of different kinds of learning mechanisms. And so I want us to kind of focus in on some of these learning mechanisms as we talk about machine learning specifically. So what does a machine learning workflow look like, And you'll see, and so like that first piece over here where we have data and the creation of testing and training data sets, we now know that there is a ton of work that happened before we got the data that you can simply split into a testing and training data set, It's important to create a training and testing data set because your training data set is basically going to teach your machine learning model from examples, potentially, and your testing data set is what you're really going to be using to evaluate the performance of your algorithm, And this is just sort of like a generic workflow. Once you've trained it, you've tested it, you've built it out, then you can sort of move your model into production where you're basically taking production data, that's data that I'm collecting about the world right now, real data, and use that to make your predictions. So I want you to keep this in the back of your mind as we're starting to go through each of these different kinds of machine learning algorithms. So when we think about machine learning models, I want you to start by thinking about them as just models, Models are ways in which we represent information about the world around us using some sort of mathematical representation and then use that mathematical representation to provide some sort of substantive conclusion, right? So you could ask a question like, what forces do we need to deter in the Soviet Union? Or what are Soviet intentions in the Middle East? But these questions are not things that you can necessarily like create a mathematical model around that's going to be very, very clean. So these are examples of what Ralph Strout called squishy problems, right? They're squishy questions. I love this paper because I think it's a really great example of sort of the complexity of problems that we are trying to use machine learning models for, right? Some things are going to be really simple, right? Cat, not cat, I think is maybe a simpler one. And I keep coming back to that example. But many of the questions that you might want to ask that I think have more serious social and political implications are oftentimes complex to begin with. And so keeping that in your mind, right? You're modeling squishy problems. So doing things like capturing uncertainty or even being able to demonstrate or communicate the bias or assumptions that you're making can help you then be able to communicate the performance of your model. But the purpose of these models is to be able to provide, right, efficient and convenient access to the information that we have about the world around us. And so what we're really trying to do is capture these states and events of the world, use them to build a model, and then now we have this stored information asset that we can query and ask more complicated questions for, right? So you can kind of see in this Venn diagram up here, you have this world phenomena, a shared phenomena exists then when you're able to actually have your machine learning model start to capture some of that information. Another really great paper that you can go and check out if you want to kind of think about what this transition from modeling the world to computational models looks like. And so there are then different kinds of models that we can create, right? So if we start at the top with models based on the different kinds of model parameters, you can have models that are deterministic, right? So we know what the next step is. Non-deterministic models involve a variety of different methods. These are often used, right, for squishy problems where you might have fuzzy decision-making or fuzzy logic involved, and so on and so forth. I'm just going to leave this map here for you to reference later. But really what we need to be able to think about is, what is the question that we're asking and use that to decide what type of model we want to ultimately use to answer that question. So let's spend a minute conceptualizing machine learning. I want to give you just a working framework to think about machine learning based on the different types of learning that we can perform. So the first category is supervised learning. This is when an algorithm is provided with training data that basically contains labeled examples, right? I give you an image. This is a flower. This is a potato. This is a dog. Unsupervised learning is then where I basically provide an algorithm with training data, but I'm not labeling it. I don't tell you what's correct. I don't actually do any sort of annotation. And really, the correct outputs are discovered. And so they're emergent. And so usually you'll be using some sort of index, some metric, something inside the data itself to kind of decide how and where to correct or how and where to cluster different kinds of things. And we'll look at each of these in detail, so don't worry about that just yet. And there are sort of semi-supervised learning methods where you can, give it a little bit of training data as we looked at earlier, and then save the rest for testing data. But that is something that, we'll talk again about as we move on to the next lectures. The third class here is reinforcement learning, and this is really where an algorithm is treated more like an agent and it's provided with feedback for correct or incorrect outputs. And so you can really think about it in terms of the algorithm is learning from experience. So let's talk about supervised machine learning. There are two main things that you're really trying to do with supervised machine learning algorithms. You're trying to classify, so right, cat, not cat, and you're trying to predict. I think it's going to rain tomorrow. There are a variety of different methods, and we'll go through a couple of these. The first thing you're going to be doing is wanting to be able to do trends and move from trends to predictions. And so this is where regression can be really helpful. And so it means that you're basically taking the different kinds of data that you have, you're plotting them, and then you're looking for some sort of trend in the data, right? This is something that you might have done in a stats course a while back. And so you're really looking to make sure that you're not overfitting, you're not underfitting, right? You're not making too many assumptions about what the data is doing. And you're really just trying to find hypotheses to be able to fit that data and find a best fit function. So you could have a task like, I want to predict the sale price for each house. And you could come and use a data set like housing prices. So I picked one from the Kaggle repository. In this particular case, I have 1,460 training data points that are basically instances of sales And there are 80 different kinds of features. So that's different characteristics of why that sale went down, right? And so if we do some exploratory data analysis and just create a heat map, we can kind of start looking at the relationships among variables. So, does the basement size influence sale price, or does the garage do fireplaces, or does a screen porch, right? And you can really start to look for the sort of like hotspots in your data to be able to say, oh, I think these are the relationships that matter the most when thinking about what influences the price during sale eventually. And so you probably want to then dig into specific variables that seem to have a strong relationship. So in this particular case, what was weird about that data is that there was something strange going on with basement size. What was up with basement size? It's not entirely clear, but it did seem to drive sale price, right? So we don't have context yet, but we're at least to start to think a little bit more about what the relationship among specific variables are. From there, you really probably want to do a regression analysis. And so you have to pick a regression, and there's multiple different kinds. I am not going to go into all of this. We just want to kind of skim over the top, right? So in this particular case, you might want to decide, do I have dependent variables or do I have independent variables? Is the relationship linear? Is it non-parametric, right? And you're really just starting to think about, well, how do I actually now want to start to knit the variables of interest together to be able to identify a trend and ultimately predict performance? Right? In some cases, you might even need to reduce the dimensionality of your data set because there's too many variables and it's all noise when you start to actually chart it out, right? And so thinking about how do I actually reduce dimensionality to be able to improve performance. So one of the tools that you could use here would be an algorithm like a random forest, which is basically just many, many decision trees. And you could use this to do things like map the relationships among variables to then be able to ultimately make predictions. So in this particular example, and I should note all of the examples are linked to tutorials that you can use to actually try these examples out, right? So in this particular case, someone used a TensorFlow decision forest to be able to identify variables of importance, reduce the dimensionality, and then ultimately be able to predict sale price. So let's look at an example in the real world, right? So this is a screenshot from Zillow. And in this particular case, if those of you who don't know Zillow is a real estate web application where you can basically go and look at all the homes for sale in your neighborhood, right? And so really they have this analysis here that you can then look at to be able to predict home values based on house and contextual data. Now, we can't necessarily double click into their specific analyses, but hopefully what you just saw can kind of give you a sense of how one might actually produce a report like this. Right? So you can decide what type of variables of interest you have. You can decide how you want to actually then train your algorithm. You probably want to start with something like a regression analysis. You might use a random forest to be able to just kind of look at some of those trends and be able to move toward predictions. The next class of algorithms really involve learning from examples. We're going to start a little bit again with probability logic, and we've encountered this before when we were talking about logic way back when. But you can really think about this as, given a certain set of variables, which ones am I going to actually use to be able to predict what the answer is? So in this particular case, we can see that weather and dental problems are independent of whether or not you actually have a cavity, for instance. Coin flips are independent as well. The next class of algorithms really allow us to be able to learn from examples. And so Bayesian methods involve using historical data, our priors, to be able to predict what's going to happen next. So you can ask questions like, what is the probability of an event occurring given a set of possible conditionally independent systems? And there are sort of two different directions in which these algorithms work. The first sort of moving forward is the diagnostic direction. So you can say, what is the probability of a cause given that a certain effect is true? And then in the opposite direction, the causal direction, you can ask questions like, what is the probability of an effect given that a cause is true? Let's look at examples. So a classic example of Bayesian learning is spam filtering. So in this case, we're asking the question, what is the probability of email being spam given the appearance of a set of words? This example is from a classic paper back in 2002 by Paul Graham that actually talked about a plan for spam using Bayesian methods. And it's a very basic way of classifying emails as spam or not spam. And so you can kind of think about this data set, right? You're extracting terms and you really want to be able to say, which of the words in this email are more likely for this to be spam? And this is especially difficult when, we have very, very complex spam emails that involve princes asking you for money and so on and so forth, right? So sometimes it's easy to detect, sometimes it's not. So if we want to engage in the task of classifying spam and not spam emails, I might want to start with a spam-based data set. So this is from the UCI machine learning repository, and it's got, or just under 5,000 training data points with 57 features that describe, different aspects of that email. And so in this particular case, which is just sort of like a toy problem that I ran through, you can kind of see how you would go through the steps of saying, okay, this is what threshold I need is to be able to determine what qualifies as spam. I can then test that threshold on my actual training corpus, and then I can actually go through and check every single email to say, okay, should I classify this as spam or not, right? But that equation that we're seeing up there is the core of a Bayesian classifier in this particular case. One of the challenges that occurs as you start to do this is that you have to reason with uncertainty. And there's a lot of different kinds of uncertainty that we have about data around us, right? Things can be insufficient, they can be incomplete. Sometimes there's just like straight up inaccuracies. And so understanding the different types of uncertainty that you have in the data, the data that you're dealing with is going to be very important when you're thinking about reporting the performance of your model. This is an entire class in and of itself, but I want you to just think about uncertainty as you're thinking about your data. One of the ways in which we can reason with uncertainty is using an evolution of the Bayesian methods that we just touched on called Bayesian networks. And these allow us to really reason between correlation and causation. So a typical Bayesian network, as shown in this example, kind of can show you both the topology and the conditional probabilities. And so you can kind of start to see the relationship between different things that you may not have otherwise thought as connected. So in this particular case, the probability of burglaries and earthquakes, and whether or not two people call you up, given an alarm. You can then sort of zoom out of this and start to represent causal structures. So, right, not just a toy problem between 2 or 3 actors, but really think about, can I create a Bayesian network to be able to evaluate car insurance applications? And now you can start to say, okay, here's all the data that I would need about, the types of incidents that occur. Here's the data I'm going to need about insurance applications themselves, what I want from the people about their own behaviors, for instance. And then you can kind of knit those together to start to create this like larger model that talks about whether or not somebody should be given a car insurance or at what rate. And this is something that's used in the real world, right? So Accenture has this really interesting report that kind of talks a little bit about how people are using different kinds of algorithms. And again, they don't talk about the specifics here, but they show you some of the different ways in which they think this can sort of impact the insurance industry, right? So the theory here is that by being able to give people more scale appropriate, background appropriate, right, blank appropriate insurance policies, you might be able to do things like lower claim costs or lower acquisition costs and so on and so forth, right? But again, it's really important to just, again, think about, right, what data are you using to drive what type of decision making? Are you biasing against the person? Are you biasing against the company? And just kind of thinking about the uncertainty also that you might have when you're looking at the data that you would use to develop something like a dynamic insurance pricing model. This is an example of Tesla's safety score, in which they use real-time driving data, including things like the use of seatbelts, turning and braking behavior, or other monitored car functionality, right? Because the entire car is basically a sensor, to be able to provide users who opt in with a dynamic insurance price, right? Both radical and scary. And so it's one of those things where, right, these methods help us start to do more complicated things and provide people with more dynamic options, as opposed to just saying, here's a one size that fits all. So there's a lot of potential for personalization, as we'll talk about a little bit later. Okay, so I'll just run through a couple of quick applications of Bayesian networks. In this particular case, you can see one that's being used to explore regulation among genes. What I think is really interesting is that the same algorithm can be used to ask very many different questions, because what you're essentially doing is you're modeling a system, a domain of data using the same way. So in this particular case, right, the Bayesian network automatically is using nodes and edges and associated probabilities to be able to then identify or discover unsuspected relations between, in this particular case, genes and diseases. right? Another example here is on the task of being able to model cybersecurity risks in an industrial control system. So on one end of the screen, you can actually see what the network control of, in this particular case, a tank reactor might look like. That data that these reactors were all instrumented. And so in that node graph that you can see, that is how the data about each of these things can be propagated through the representation as a Bayesian network. They introduce fuzzy probabilities to account for uncertainty. And then at the bottom, you can kind of see a curve of the dynamic cybersecurity risk, right? So this paper can give you a good insight into an end-to-end model of how you could actually use, in this particular case, a Bayesian network to reason with uncertainty and ultimately be able to engage in some sort of risk management task. But there's a lot of limits when you start to think about optimization alone, right? So we oftentimes will talk about optimization and convergence problems using this sort of graph, right? And it kind of shows you how you might have an algorithm that performs really well with a certain amount of data, but eventually you might actually hit some sort of local maximum or a local minimum, which is difficult for the algorithm to train out of unless you provide it with more data. And so in this particular case, right, the goal is always to be able to find the global maximum, right? The global maximum performance of an algorithm. And that's going to vary depending on what model you're using, how much data, the diversity of your data, and many, many other factors. And so people have started adopting what are known as ensemble methods to basically be able to boost performance. And this is an entire suite of methods in and of themselves, but you can kind of think about them as, right, you're picking a couple of different algorithms and you're putting them together to be able to, in effect, boost performance. So in this example, I have a naive Bayes classifier, which is super basic. And then I'm basically using a second filter to be able to say, okay, those things that I'm catching as spam or I'm saying I think are spam, I'm just going to double check to make sure that I really am feeling accurate about this. And so it's a good way of being able to sort of weed out false positives or false negatives depending on how you design it. There are many, many ways to do ensemble methods. I have a brief summary of the full suite of techniques that you can use, whether you're voting or boosting or stacking or doing some sort of cross-validation, right? Ultimately, you can think about it as you're taking a set of different models and either having them compete or collaborate or work together in some other way to be able to give you a better result than you might have with just one model, right? This is sort of a best of breed approach. Let's now look at the second category of machine learning methods, in this case, the unsupervised machine learning methods, where really the algorithm is provided with training data and correct outputs are discovered. That is, they're emergent. So you can use unsupervised machine learning methods to do things like clustering, where you're grouping similar data. You can do things like dimensionality reduction. So, thinking about spaces where you have a lot of different variables, and you might want to actually understand like which of these variables are the actual like influencers in the model outputs. You can do things like think about relationships among variables, so doing association tasks in a lot of ways. So lots of different methods exist in this space, and it's an entire course in and of itself, right? Like many of these different topics. And so I'll just cover a couple of examples so we can kind of see how they might stack together to allow us to perform different kinds of tasks. In a lot of ways, we're really looking to learn from patterns, right? We're clustering data to be able to look at groups or different types of themes that arise from it. But because of the sheer number of methods that are out there, it can be a little bit overwhelming sometimes to try to figure out where to begin. So in this particular case, we're actually looking at just a quick visualization of some of the clustering methods that are available in the Python package scikit-learn, which is popularly used to perform this genre of machine learning tasks. So a simple place to start is usually a k-means clustering algorithm, where k is really just the number of groups that you want to break up your data set into. And clusters are created by associating observations with the nearest means, and then really just doing like a simple calculation of like, where is the center of this cluster, and then separating it into these tiny little groups. And so you can group into 1 means, 2 means, 3 means, right? So you can really start to think about the number of different buckets that you want to split up your data set into. And of course, it's important to remember, right, that the more buckets you split up your data into, the smaller those buckets may get. And so you may want to decide where and how you want to split up your data to actually have the most value, right? Find the most meaning in your groups. Let's look at some examples. So in this first one, our task really is to identify themes in Bob Ross paintings. This is an example that was done by Walt Hickey from 538, which is a popular data science blog. And you can see that he basically took a corpus of Bob Ross paintings and then ran a k-means-based cluster analysis of them to identify what some common trends were with them, right? So you can see 91% of Bob Ross paintings contain at least one little happy tree, which I'm glad to hear the data supports. In this case, he has 3 different clusters that emerged, and it can allow us to then start to say, like, what are some common patterns that we can see in a specific data set? If we take a similar approach to looking at user interfaces, you could actually extract a color palette from a user interface mockup, right? So if you look at the image of this UI, each pixel has a color, and so you're basically looking at the most popular colors in effect that appear in this particular user interface. It's the same sort of technique that you might even use to, for example, take a photograph of a landscape and then extract the palette of that landscape and then use that to be able to design a subsequent user interface. In a lot of ways, what you really want to do is start to move from just clustering to more probabilistic reasoning. So dimensionality reduction is a task that is commonly performed at this stage when you have this high dimensional data and you want to be able to reduce it to some sort of meaningful representation, right? Data isn't always as clean or neat or small as we'd like it to be. Sometimes you have high dimensional data that have a lot of attributes, so lots and lots of features, or lots of observations, right? So lots and lots of instances. And so the image that we're looking at here, it's actually a corpus of handwritten digits. And in the visualization that we have of that digits data set, right, you can kind of see it looks a little noisy. It's pretty much impossible to be like, yes, that yellow cluster, those must be all the number 4 written by hand. And so you can use different methods to start to then try to think about how to reduce the noise or that complexity of your data set. So let's look at principal component analysis as one of the methods that you might use to actually then start to drill into your data set a little bit more. And it's one of the most popular techniques, quite frankly, used for this type of dimensionality reduction that isn't a neural net technique that we'll look at later. So in this case, our task is to identify customer segments from grocery data, right? So somebody basically put together a data set of 2,240 right, data points that include what people bought where with what promotions and so on and so forth. And so they were able to then cluster that data to be able to, in this particular case, basically get consumer profiles, right? So cluster number 1, definitely a parent, have these many members of their family based on their shopping trends. And so you can kind of see a simple example of how you might be able to take that kind of data and first start to then do a k-means clustering and then use the PCA to identify which of the variables within the data are the most influential in being able to actually help us create meaningful clusters, right? So in this case, the number of people that they have in their family, whether or not they're a single or a married parent, the age of their children, and so on and so forth. Here's another fun example. In this particular case, and there's actually an entire book about whiskey flavor spectrums. But in this case, one of the graphs that they have was a whiskey flavor-based product segmentation, right? Sometimes it can be a little bit hard to delineate between the different flavors. And so in this particular case, they've taken attributes of the drinks themselves and then created a hierarchical classification of, in this particular case, right, all the single malt whiskeys of Scotland on the basis of flavor profiles. And you can see these 6 clusters that they've identified. And if you're so inclined, you're welcome to go and actually taste test this to verify and validate their results. In this book, they also talk about then using that same approach to be able to, right, do a PCA-based analysis. And now we're looking at a PCA-based analysis of 158 malt whiskeys. And so what they're showing us is how different groups of drinks are able to then, right, represent the different flavor profiles that you might expect from this class of beverages. Right? And so you can kind of see the product segmentation, customer segmentation are popular early tasks that we used to use this family of methods for, but it's now, there are lots of different things in the same vein of probabilistic reasoning that you might be able to use a k-means clustering for, as well as in a PCA. And quite frankly, we'll oftentimes use it even just for exploratory data analysis, right? Just dig into a data set and just understand a little bit of like, what is the lay of the landscape right now? I'll show you a couple of more complex examples just so you can kind of see the power of this, but I don't want to go into a lot of the math underneath this because it's fairly complex. But in this particular case, we're looking at somebody using a set of ensemble methods, right? So that's a group of different methods put together, right? Either cooperatively or competitively put together. But in this particular case, we're looking at a toy data set, right? So this is the iris data set from the UCI machine learning repository. And they're just showing us how they can use this variation on the PCA method to identify groups of flowers in this particular case. And so you're able to then get this representation of the iris data set that allows us to say, yes, this, these black ones are one group of flowers, the gray are the other, and the white are the other, based on the constituent components of that data set. And they use this same technique to then look at breast cancer data and actually be able to identify critical breast cancer subtypes. And so it's a really powerful technique. And so if you look at the entire research paper, you'll see all these different variations on this base family of methods that they used that are in effect, clustering methods and then some, to be able to look at this very complex, very different kind of data and be able to perform the segmentation to allow us to learn something particularly radical, right? In this particular case, the different disease types that might exist. And so there's a very powerful family of methods that I feel like we oftentimes these days, overlook, but I think it's worth revisiting and remembering that, when you have a complicated data set, this is a great place to start. But not all data is just, cat, not cat. A lot of times we have sequential data, ordered data, time series data, text, speech, and even video as data. And this is stuff that is changing over time. There's a temporal scope to it, but it could even just be, it's a sequence over time. And so some examples might include daily weather observations, supply chain workflows, even bird songs, right? Audio data is an example of sequential data. Once we start getting to these more complex forms of data, it becomes really important for us to understand what the spatio-temporal scope of our data is, right? How much space is it covering? What time is it lapsing over? What exactly is the unit that the data is covering? And that then allows us to start thinking about learning from sequences. Let's look at a simple task. In this case, we want to predict the likelihood of somebody engaging the single type of personal workout sequence. And so what we have at the top is, the number of times they've done each of these different workouts. And then we can start to ask questions like, in a 3-set workout, how likely am I to do a run, do push-ups, do pull-ups? And so then we can create transition probabilities to depict transitions between states in the chain as a form of conditional probability, right? So this should feel a little bit Bayesian, but we'll start to do something a little bit funny as we move through this data set. You can then use that representation, right, those probabilities of transition from one state to the next, to use what's known as a Markov chain. A Markov chain shows us, right, how likely you are to go from running to rowing and so on and so forth. Markov chains are, again, a fundamental component of many modern machine learning algorithms. And so I pick on this one specifically because I think it might be powerful even when you start to chain together things that are more modern. Hidden Markov models are a similar family. So you can take then that Markov chain and you can then represent processes that can be in more than one state. And so you can start to introduce concepts around uncertainty of the system. And really, hidden Markov models are used to solve sort of 3 basic problem types, right? You might want to evaluate an event, so the probability of an event occurring given a sequence. You might want to do things like path optimization, right? So what is the optimal set of model states? Or even just parameter estimation, right? So being able to say, okay, given the different kinds of model and empirical observations that I have, what are the model parameters that then best fit those observations? And so, you can use this pair of methods to then be able to analyze different kinds of sequential data, right? If we kept running with our workout data, you could then start to do like a workout prediction algorithm. But I'll walk us through a much more common example with these 2 methods, and that is from signal processing. So this is actually one of the earliest attempts at doing machine speech recognition using hidden Markov models. It's a really great paper because it kind of shows you the way in which language processing has evolved in a lot of ways, right? And so in this particular case, we're looking at a block diagram depicting a more pattern recognition approach to continuous speech recognition, right? So you have speech, you analyze the features, you match it to things that you know, and then you say, okay, I think this is what is actually being said. So they took a data set of people saying numbers, right? So numbers like 6, 5, 32. I think there were actually only digits, so 6 and 5. And they actually processed it to then say, can we actually define a signal where you're thinking about it in terms of silence, speech, and then use that data set to recognize which word is spoken. So on the left, you can kind of see a block diagram that shows how they would isolate an individual word in this recognizer algorithm. And then on the right, you can kind of see what the average rate of performance is for different kinds of speech recognition models of this genre. Right? And again, the paper is a great resource if you really want to learn how hidden Markov models work from fundamentals in a real example. You can take that same approach to then ask and answer different questions that are very, very similar from a sequences perspective, right? If you want to be able to model market volatility based on the price of gold, you might take gold spot prices from 2008 to 2020, and then use that same family of methods to be able to say, well, what is that market volatility, right? So on the top, we have those gold prices, and at the bottom, you can see that volatility visualized. A lot of the examples that I'm showing in here, this is just a quick aside for if you'd like to dig in more into these examples, are linked to tutorials that you can actually follow through and try yourself. And so I would strongly encourage you to pick at least a couple of these to go and try out, even just for your own learning. So that way you understand exactly how these algorithms work and what types of packages are commonly used to be able to do something like this, as well as the data sets being available. Here's another example in which somebody, again, uses a hidden Markov model, but this time to forecast earthquakes. And so there's data that they're using was seismic activity, right? Historical seismic activity in California and Western Nevada from 1932 to 2004. And then they ran it through this model to be able to retroactively issue a series of forecast probabilities of different kinds of earthquakes, right? And so in this particular case, right, they were able to actually verify their results because it's already happened. And so they were able to, right, see that the forecasts were close to their observed seismicity in that during that particular time period. And so there are really nice ways in which you can actually try a technique, try an algorithm using some historical data or data where you actually know what sort of the right answer should look like. And that is a nice way of actually learning whether or not the technique is actually allowing you to improve on the state of the art or able to give you surprising results when you're still sort of exploring new data sets or even new techniques. A lot of this work has been applied in recommender systems. And so from here, I really want to just show you some different applications of this specific genre of AI, right? In a lot of ways, we've been asking the question, right, how do we personalize search results for a very, very long time, right? We go to Google, we look something up, and what we really want is, yes, some generic information, but ideally information that answers our specific question. And so there are a couple of different types of recommender systems. The first is a content-centric system. You can think about this as a recommender system where, yes, there's a recommendation for you, but the recommendations are based on similarity among the different types of data points, right? So in this case, you can almost think of it as that clustering example all over again. So if I enter the artist Sufjan Stevens into the music map tool that I'm showing you here, it shows you at the center, there's the artist that I've chosen, and here are the nearest neighbors to that particular artist, right? So the recommendations are based on, what types of music those bands are playing and other characteristics about the music itself, not about me as a person who likes this music. There are lots of other ways in which you can then kind of play with this. I love this little set of examples that I'm giving here. When I was in college, I would go to Gnod's World of Music and look up new bands this way. So this is sort of like pre-modern music recommendation systems. But it means that, it demonstrates that it wasn't just looking for similarity between two data points, but, you can even do something like say, here are 3 radically different bands that I'm interested in. Give me some recommendations for music that might be based on that set of choices, right? So content-centric doesn't just have to be most similar to a single instance or a single observation, but can even be most similar to a family of observations as you start to learn more and more about my taste preferences. It allows us to also then think about how to represent information to users in a meaningful manner. The same guy, Mark Gebney, who built the Gnod project, also built this product chart, which I think, again, just nicely visualizes how a context-centric recommender system can work, right? In this particular case, it's grouping them based on similarity given a set of parameters that are chosen. right? And you should already be feeling a little bit of familiarity with this method of visualization, because this is how a lot of shopping apps will even work, right? You're being presented with things that are most relevant or most similar or most popular, right? Depending on what type of centricity we want with our recommender system. But increasingly, right, we've moved to user-centric systems, things that are based on what the system remembers about me specifically. So if we look at this particular example, there's a really interesting paper that actually looks at, they actually measure personalization in web search. At the top figure, you can kind of see what that advertising ecosystem looks like, right? So really, in a lot of ways, when we engage in free search tools, we're providing a publisher with some sort of information about ourselves, and then they use that information to then decide which types of ads to serve. And so if you look at the bottom, you can start to see that my previous searches might influence my future searches. And so in this paper, they used a couple of examples to kind of show us how different categories of data influence the type of search results that we might get, or even the types of features that are given to a user downstream. It's a very powerful method of beginning to start to set the scene for collaborative filtering, right? So if data is being collected about each of us and how we are interested in or disinterested in different kinds of products, there's a lot of information about our user behavior. It means we can start to make recommendations for each other by each other, right? Based on your preferences, not just in one product category or in one type of thing, right? Based on your profile, I might be able to start to make recommendations across product segments, for instance. And this is, for better or worse. Amazon is a classic example of a platform that uses a lot of recommendation engines under the hood, that do cross-product recommendations, that use a lot of historical data, both about me and other people, in order to then make what it thinks are very targeted recommendations, both for things to buy as well as ads to serve. And it's been a really radical change in the way in which we shop, the way in which we engage in commerce. And I think it's sort of also left a lot of open questions about the ways in which we want to engage in buying and selling of products, or even giving each other information that we think is important, relevant, and timely. And so this big question keeps coming up around, what should we be personalizing? This is an interesting presentation that someone from Netflix actually gave that talks about trends in personalization. And you can kind of see the different types of things that they're personalizing in just the Netflix user interface, right? It's not just the movies to recommend, but it's even where to put things, what type of content to use, how to present it to you. Everything is a recommendation, as they say. And, I thought it was an interesting stat that over 80% of what people watch comes from the recommendations that they're making. And so even though recommendation systems have existed for a long time and built on many of the methods that we've talked about, both supervised and unsupervised, it still remains a really open problem because personalization is very hard, right? There's a lot of different attributes about both users, about the data itself. Helping actually do that matchmaking is a really complex problem. And of course, there are many, many mathematical challenges with then also making sure that we really are giving people the correct recommendation for the question that they're asking. And so the problem space is still very wide open. And I think there's a lot of really interesting things that we can still ask and answer within the space of recommendation systems. I'll just show a couple more examples of just sort of the way in which recommender systems are changing. Here's an example from Spotify. And you'll see again, right, even though their their core business is recommending music for us to listen to, even their most recent user interface update moved to a newsfeed model where they're starting to also now recommend content of other forms about artists, right? Sometimes it's almost like transitioning from just delivering the music to the entire ecosystem around the music. And so it is now deciding what types of things for you to actually consume that are more than music within this new interface that they have developed. And so it really sort of, reminds me of the question from High Fidelity, if you ever watched it, right? You have a crotchety old music shop owner who asks the question about what influences what, right? Did I listen to pop music because I was miserable, or was I miserable because I listened to pop music? I think the way in which we've been making recommendations has changed over time. And it's really important for us to kind of think a little bit about the causality of how and why we make the decisions that we do. And so recommender systems really introduced a couple of concepts into sort of the public conversation. The first was around this idea called algorithmic bias. And so I argue that there are limits to recommendation systems due to algorithmic bias. And I'll give you an example again on the sort of theme of music that we've been kind of running with from Pandora. About 2014, and even before that, I remember, signing up for Pandora when I was a kid and thinking this is going to be the most radical way of engaging in music recommendations, right? I've been using Nods to look up bands. Pandora came along and they said they have sophisticated taxonomy of music information, 10 years of analysis by trained musicologists. So I was like, oh my goodness, it's basically an expert telling me what music is out there that I could listen to. And they introduced this concept of the Music Genome Project, where they were analyzing different kinds of musical characteristics and so on and so forth. And as their data set grew, and as this entire recommendation space blew up, they actually started to transition, right? And so you can see in 2014, they claimed Pandora does not use machine listening or other forms of automated data extraction. And if you look at the contemporary edition of Pandora, it is built on machine listening and automated forms of recommendation, right? And there's nothing wrong with that, right? We have a really rich data set. You have lots of input from different kinds of users. There's a lot of collective feedback. There's a lot of information that does still exist about, right, the data itself, about the songs itself. And we're able to generate more and new and interesting types of music analyses methods. You also have a lot of individual engagement as people create and curate playlists, right? We're now we're making mixtapes on the internet. And that means now you have a far more robust data set of what sits with what inside human musical tastes. And that allows for, in this particular case, a company like Pandora to be able to deliver highly targeted advertising. And so it means that there is this sort of potential for being able to nudge people in specific in specific directions. The Pandora chief scientist actually was quoted as saying, it's becoming quite apparent to us that the world of playing the perfect music to people and playing the perfect advertising to them are strikingly similar. And so you will notice, right, this push towards both providing better recommendations for the core thing that people are interested in, but then also, right, providing different kinds of advertising. And while it's often fairly innocuous, right, it's just, here's a more fun beverage for you to consume, there are also slightly darker ways in which this can present, right? So Pandora, for instance, had a political ad targeting system that was used during different presidential and congressional campaigns. And it really was, in this particular case, just presenting to users that listen to particular types of music, particular types of ads. And so it was making assumptions about what type of political leaning you may have based on what kind of music you're listening to. This also means that there are a lot of different kinds of limits on privacy itself, right? If you think about a quick framework for thinking about privacy with respect to data, there are three things that really pose these privacy challenges when we start to think about aggregate data collected about people across the globe. The first is this concept of data persistence, right? So once data is created, it might actually persist longer than me or the person that actually built it or created it. There's data repurposing, where I don't know exactly how my data may be reused in the future, right? So we just saw an example where I thought I was, thumbs upping music so that my friends could get better recommendations, but I was also inadvertently helping fuel an ad targeting system. And then there's also data spillovers, where even though I might not be explicitly recording your information, the fact that I'm connected to you and have data about you might create data about you, whether or not you intended to within the system that I'm using. And so this creates a lot of complications when we start thinking about data and privacy, especially in sort of this, era of big data and this era of data-driven machine learning. A classic example of how all this can come to a head was the Facebook Cambridge Analytica scandal between sort of 2014 and 18. And so if any of you were using this particular platform during this time, you may have gotten a notification that said, how can I tell if my information was shared with Cambridge Analytica? And it sort of came out that it was sort of based on just user input in a quiz app, like, what do you like sort of quiz app. And so if we think about the kind of information that might be encoded in a quiz application, it might be, what kind of, what's your favorite puppy, or what kind of foods do you like, or what type of music do you listen to? During the trial that followed this particular scandal, it came out that there were messages like this that were sent among participants in the scandal, because they knew that they were able to actually extract these derivative analytics based on the original data that was collected about people, right? So you could do things like infer what a person's political view was, how fair-minded they might be, how open to self-monitoring they were, and so on and so forth. And so it means that when you start to pair big data with these really powerful questions, it sets the tone to do some fairly disconcerting things. And so in this particular case, the problem really was that private Facebook user data, including the data of other people, was leaked and repurposed then for political strategy. And so when the whole thing kind of shook out, the part that always troubles me about the story is that this was data science writ large being used to then influence the way in which people actually act or behave in civil society. And so it's really important for us to just really think about, who are we giving our data to? How are we allowing our tools to actually then repurpose that data, and really thinking about the sociopolitical context of these types of machine learning systems that we use and build. Things came to a head with this particular instance, and it's not the first time, nor will it be the last time, that we see folks within the tech sector having to defend the way in which we design different kinds of systems, including the way in which we design AI systems. This comic strip from the New Yorker always makes me chuckle because in 1993, they said on the internet, nobody knows you're a dog. And in 2023, we asked the question, remember when on the internet, nobody knew who you were? It really demonstrates to me the power of what the internet has done when it comes to thinking about what kind of data we have about each other, about the world around us, and about sort of what we would like to be able to do in the future. It's both a really powerful thing as well as a really dangerous thing. And I think it's really important for us as designers of technology to really think a little bit about exactly how we want to support individual privacy while still being able to promote the ability for us to be able to integrate insights across different kinds of data and different kinds of landscapes. So now let's turn to the third category of machine learning algorithms, reinforcement learning. These are algorithms that are really, agents, in effect. They're provided with feedback for correct or incorrect outputs, and they learn from experience. There are sort of two general ways in which you can kind of think about them. One, which is model-based, where the environmental model is actually provided, or a model-free algorithm where everything is emergent, in effect. And to be perfectly frank with you, this is a rapidly advancing space, and there are many ways to categorize these methods, and it is a little bit the Wild West right now. And so I'm not actually going to go into a lot of these methods in particular, especially since many of them actually depend on or are being used in collaboration with neural networks. And so I'll integrate some of the details about how these methods work when we go into talking about neural networks in the next lecture. For now, I just kind of want to give you a couple of quick notes so you can kind of park it in your brain, know where it sits in the sort of set of methods that we're talking about in this lecture. So in reinforcement learning, we're really thinking about how to learn from experience. And so this control system graph should feel familiar to you. We saw it all the way back when we were talking about cybernetics, right? But it's really this idea of how to introduce feedback into the process that our algorithm is engaging in. And so the feedback in this particular case is provided in the form of a reward. So an agent performs an action in a particular environment. Once we understand the state that it is moving into, there's a particular reward that is afforded, and that either enforces or reinforces the actions that that agent performs. There are lots of different applications of reinforcement learning. This is actually a really interesting set of tutorials that OpenAI created called Spinning Up Reinforcement Learning, and they're linked in the slides. But you can see in this particular case, a robot learning how to actually move in a simulated environment. And so there's different sort of feedback mechanisms under the hood that then help it figure out where its legs should be going and how to kick a ball and so on and so forth. In this particular case, you can then see that same sort of approach being brought into robots learning real-world actions. And so you can provide a specific goal, give rewards when the goals are met, and really then sort of let it run through several iterations to see if it ultimately is able to actually perform the tasks that you're really interested in. And if you actually watch this video all the way to the end, by the end of a series of iterations, the robotic hand is actually able to spell out a word of interest. And so there are a lot of different kinds of algorithms, as I mentioned. These are some of the high-level buckets that you can really think about, right? There's a lot of conversation around policy. So what kind of rules should you give the agent to work with? How should they learn? How should they look at the environment? How should they take that environmental data and then use that to also learn and make decisions? And so there's lots of feedback among the rules, the learning methods, the environmental data, and so on and so forth that an agent actually has to use to be able to learn from experience. And so we'll come back to this again with neural networks, but really at this point, you're kind of looking at that entire set of things, right? There's a knowledge base, an inference engine, a learning mechanism, and even a user interface that are now beginning to get integrated into these larger models, right? So they're models of models. And so let's just spend a few minutes sort of defining agent systems, because this is going to be probably the most productive framework that you can use for thinking about AI systems moving forward. So we define an agent as anything that can be either viewed as perceiving its environment through sensors and acting upon that environment through actuators. These sensors could be digital sensors, so me entering data in through a keyboard, or it could be physical sensors like a camera pointing at a bird. And so there are different ways in which you can actually get data in. And so agents can perform different kinds of tasks in different kinds of environments. And here are a couple of helpful examples, I hope, that can kind of show you the variety of things that different kinds of agents can do. So a part-picking robot can actually put together parts and build, for instance, a car. A medical diagnosis system might take in data about patients and help make recommendations around how to go through diagnoses, or maybe make some recommendations for different kinds of tests. An interactive English tutor might even just take keyboard or voice entry input and then use that to be able to help students understand how well they're learning a language and be able to give them feedback and help sort of teach in that particular environment. And regardless of sort of what the environment is, there are lots of different ways in which you can start to sort of categorize it to then determine what type of machine learning algorithm, what type of task, and how you might even want to set up your system. Let's go through a couple of these. You can think about environments as either fully or partially observable. So what can the agent actually sense or see, right? Can the car see the full road or just sort of a very limited field of view? Is it a single or a multi-agent? Do you have a single robot tractor roving through a field, or do you actually have a swarm of small harvesters cooperating to be able to actually harvest a field? You can think about how deterministic it is. Is it actually something where we know what the next action is going to be, or is it random and we're just letting the agent sort of freeform explore? Are we experiencing an environment that is episodic or sequential, right? Do you have seasons that you have to deal with? Are there dependencies among these actions? Is there any modularity in the environment itself? Then you can also think about sort of the dynamism of the environment, right? Is it a highly dynamic environment where things are changing all the time, or is your agent really just sitting in a closed room and engaging in a single repetitive task in a fairly static environment? You can also then think about the time step. So is it discrete? Is it continuous? Is it something where there is no clear start or stop between one phase or the other? Or is it something where, you're really just driving down a road? In a lot of ways, right, there's a lot of knowns, there's a lot of unknowns, and we're really asking the question about how much can our agent actually know, right? What can we actually codify as programmable heuristics? And each of these different factors are different ways of thinking about, right, what can or what does an agent know about the environment in which it is performing a specific task. So a simple reflex agent is the most basic form in this particular case. It takes in input about the world right now. It says, what should I do next? It goes and does the thing. Whack-a-mole game is a simple example of how that might work, right? I know where the mole is, I go hit it, it resets, we keep going. A model-based reflex agent is one, right, that has a model of the world around it. And so we can ask the question, this is my current state of the world. What's the world like right now? It adds data into that model that it is building of the world around it and using that to then inform its next steps. So in this particular case, the ghosts in Pac-Man are actually, right, these little agents that are learning about the world around us. They know where I am. They know what I've eaten. They know where the cherries are, maybe. And then they go and make their decisions about exactly how to hunt me down while I'm playing Pac-Man based on their model of the little universe that we have in front of us. From there, you can have a model-based, goal-based agent. So not only does the agent have a model, it also has goals. It's not just looking for a single thing to optimize, but you might actually have something like, for instance, the goal of creating a dynamic universe with people and characters having social interactions. I don't know how to describe The Sims anymore, right? But I'm sure many of you have played games that involve, right, virtual characters doing different kinds of activities and life events. And so the game's goal-based agent operates the Sims that aren't you to be able to pursue individual goals, right? All of your other characters, those non-player characters, also have specific personal aspirations that they might have to follow in order for the game to feel fulfilling. From there, you have model-based, utility-based agents. And so, right, in addition to the model, you might actually think about a utility function that decides or helps the agent decide when it should be doing more or less, or when it will actually be satisfying its conditions for existence in that particular space. An example of this in action would be the video game Civilization, right? So in the Civilization series, we're actually building a civilization, and our goal is to be able to maximize overall utility. And so we have lots of different choices around like resource management and diplomacy and military strategy, and so do all the other characters. And so the agents that I'm playing against will actually have to have that similar utility basis. So that way they really are thinking about it in terms of like, expanding their empires and consuming all the resources or whatever it is an AI agent chooses to do with its civilization. And from there, we can really then start to abstract and think really about general learning agents, right? So it's not just a single task or a single goal that's driving, but there's really this learning element that helps the agent then decide, what am I looking for? What kind of performance standards do I need to meet? There are all these learning goals. It feels a lot like how we might even set up a learning environment for ourselves. And so, in this particular case, there are a lot more moving parts, and we have a lot more choices about exactly how to provide feedback, to allow for change, to codify knowledge, and even to be able to say, make a decision about exactly what to do next. And this is sort of roughly the tone that I want to set for the entire next lecture that in which we'll be talking about neural networks, because a lot of it sort of uses this as a framework for thinking about the development of different kinds of AI systems. An example of this in action would be in this StarCraft 2 game playing example. And so I'll just quickly walk through exactly what happened here. So StarCraft is a real-time strategy game, and you basically have these futuristic units, and there's battle happening. So you're really just, it's video game war in space, right? And you have lots of different sophisticated AI opponents that are supposed to then actually try to battle with you. They have their own strategies, they have their own tactics based on gameplay data or maybe even past encounters with human players. And so what happened a while back, I think this was in 2019, is Google built an algorithm called AlphaStar to basically play against the top esports human player pictured here. And so they pit the two against each other, human versus the AlphaStar algorithm, where the AlphaStar algorithm was a neural network with lots more details to come in future lectures, right? But it was in effect a neural network. And you can kind of see how it is optimizing and activating different parts of the neural network in order to then decide, when to build, when to fight, when to run, and do all of the same kinds of things that a human might do while playing a game like this. It did resoundingly win. It was a very effective demonstration of the power of neural networks. AlphaStar was building on AlphaGo. If you have remember from history, there was a period of time where we had computers also play chess and Go and other sort of more tabletop games against humans. And again, those were always really great demonstrations of progress that was being made in AI systems. And so AlphaStar was an evolution of that sort of family of game playing evaluations of AI tools. But you can kind of see, again, right, a little bit of the types of things that it was considering as it was deciding what activities to do next. So the long story short at this point is that there's a lot of models out there. You are not going to have a lack of options when thinking about how to design a machine learning system or even an AI system. And so the big question is, how do you choose among models? There is unfortunately no simple answer, but I can give you a couple of notes on at least how to think about this space. So we've seen supervised learning, right, where things were learning from data with labels. We've seen unsupervised learning methods, right, like that clustering stuff that we saw earlier, where we're looking at data without labels. And then we just quickly ran through some reinforcement learning concepts where we're thinking about, right, tools that, agents that require some feedback in order to be able to learn. And so the first thing that you can start by doing is thinking about what kind of data you have, whether you have data with labels or data without labels, whether you have any rules that you can actually use to then guide learning, and hopefully be able to provide some sort of reinforcement, or if it really is just like a wide open space and there's no clear heuristics that you can codify. Then you can also think about, right, your task. So I tried to take a task approach when showing you the examples throughout this lecture. So that way you can really think about, right, what do you want the machine learning system to do, right? And so if you want to see if there are natural clusters or dimensions in the data, you might start with an unsupervised learning method, right? Really just exploring your data through clustering and so on and so forth. But if you want to learn sort of what actions to take in different situations, right? So thinking a little bit about some of those recommendations, you might then want to ask, right, whether or not it's an active or passive recommendation, and use that sort of train of thought to decide whether or not you may want to use supervised learning or reinforcement learning. The big sort of differentiators here that I want to kind of point your attention to in this graph are the pieces around the amount of data, right? So there's a question in here that says, do you have access to data that describes a lot of examples of situations and appropriate actions for each situation? Or will the system be able to gather a lot of data in the process? And if the answer is no to both of those, right? If you don't have data, if you don't have appropriate quality data, machine learning is probably not going to be a useful place to start. You may actually want to go back to the drawing board and think about what kind of data is out there that you can use to start to answer the questions that you're really interested in asking. There are lots of these sorts of guides out there. I just picked two that I thought were interesting and hopefully give you a place to start when thinking about how to disambiguate, right? How to reason among the different kinds of models that are out there. In many ways, we build models to ask and answer hypotheses that we have. All models are therefore technically wrong because we can't always capture every single piece of information about the world around us, but many, many are useful. George Box is a statistician who is often quoted as saying this, although this concept has been said by many statisticians over time, right? And it's not to say that your model is ultimately wrong and should not be used, but really the question that we're trying to nudge us towards is, right, how can we make our models more useful? They're not perfect, but all we're trying to do is create a model that represents the world around us as we know it, right? We might be able to sort of have an experimental design that creates some data that allows for us to then be able to answer some small questions, right? But remembering that these models are changing, these models are imperfect, allows for us to then even be able to reason about where the model's recommendations may start to end and where we might need to then pick up with other ways of thinking about the world around us. And so I just encourage you to think about models and machine learning as productive ways of interrogating data, but not necessarily always the perfect answer machines, right? These are imperfect tools. And so from here, we really have like a fork in the road, right? There are different ways in which we can think about machines that learn. This is IBM's Chef Watson model that was really sensational when it first came out because it was built on this giant corpus of data, right? This was the ultimate big data driven machine learning example of its kind at the time, right? This was in 2015. It was built with 10,000 recipes and, a lot more data than I could possibly even imagine. But if we look at what's happening now with the introduction of, the reintroduction of neural networks, there are a lot of emerging ways in which we can accomplish the same goal using very different ways of representation, using very different learning mechanisms. So this example that I'm showing you here is just an AI-generated pizza recipe. And so this is a recipe generator that is built on top of ChatGPT, a large language model. And so as the core algorithms that are available to us are changing, so too is changing the way in which we're building these kinds of systems, the way in which we're thinking about data, and even the way in which we're sort of reasoning among the models that are available to us. I really wanted to go through this sort of series of lectures talking about machine learning and other methods to just encourage you to think about things beyond neural nets, because many of those methods will come together when we start thinking about how modern AI applications are built and what what each of these different ingredients can do to be able to either bolster, boost, or improve the different kinds of models that we create to answer whatever questions we're asking about the world around us.